All right, let's start. Okay, so last time, we are studying, from the last class, we are studying interval estimate, right? And then, so we started from the situation where we assume that the variance is known, and in that case, we want to obtain the interval estimate for the sample mean, okay? And then the sample mean will be also the Gaussian distribution, and then we basically change it to, we basically change this sample mean into a standard normal distribution where the mean and the variance is 0 and 1. So that way we obtained the range of of this true parameter mu, which is our mean value. Okay, and in this case, since this guy was our standard normal random variable, so we used the standard normal distribution, and then we did also a one-sided interval estimate, right, where the lower or upper part is kind of unbounded. Okay, and then we also studied some example where we can obtain some minimum required number of samples in order to obtain a certain length of our interval for our estimate, right? So in general, if this length of the interval is smaller, and then it will be like a better estimate. So that way we want to ensure that our interval is within a certain amount, and in that case we can obtain the minimum number of samples. So in general, if the sample size gets bigger, and then this interval, the length of this interval estimate will be smaller and smaller with the same probability or same confidence level. Okay. And then we switch it to a little bit more difficult case where the variance is an unknown. So in this case, we use a sample mean. Still, we want to obtain the interval estimate for sample at the true mean value. Okay, so still we are estimating the same parameter, but we do not know the true variance. So in this place where we used true variance value or the standard deviation, we actually changed it to the sample standard deviation. Okay, so by just simply replacing that part with our kind of inaccurate, just an estimate value of our sample standard deviation, and then this guy, which used to be a standard normal random variable, becomes now a t distribution or t random variable, and thus it's just a matter of changing kind of table that we look at in the back of your book. And so instead of using this Gaussian distribution, so we will use a little bit thicker tailed t distribution. And then also t distribution had a parameter where the which is the degree of freedom, and then the degree of freedom is set as the n-1, where n is our number of sample, right? And then we derived how we can obtain this guy to follows the t distribution, right? So that's what we did last time. Okay, so you have to closely follow and be really familiar with these proof, right? Coming from this definition of a t distribution, and then matching that with this form that we use, in order to obtain the interval estimate for the true parameter mu or mean value when the variance is an unknown. Okay, but the overall story, back to the overall story, this guy will follow the t distribution, and then the remaining story will be the same. So given 95% of the confidence level, if it is a two-sided interval estimate, and then t distribution will have this parameter value. And then the story will be the same. And then if we manipulate this guy, and then we obtain this, right? And then we finally obtain this interval estimate for this true parameter mu. Okay, and then so one thing that I wanted to mention was, let's compare this guy with the interval estimate where the variance was known. Okay, so in that case, mu was x bar plus minus, and this one will become z, and alpha over 2 times what? Sigma divided by sigma over square root n, right? And then what is changing part when determining this interval estimate? So depending on our sample, we will obtain different interval estimate. But here in this representation, this guy and this guy was fixed, right? And then the only changing part, depending on our sample, is this part, right? Okay, and then let's compare this guy with this. And then this part will be the same. And then this guy changed as a t distribution, of course, right? But at the same time, n is fixed, but this s will also be dependent on our sample, right? So it is no longer a fixed value. It can be larger or smaller, right, depending on our sample. So in general, so let me ask this question. Given the same alpha value, which one will be kind of a larger value? So suppose alpha was 5%, and then this part will be 2.5%, and then in the case of z, or standard normal distribution, this value was 1.96, right? But what about the t distribution? So in general, Gaussian will be having a more narrower distribution, and then t will have a little bit thicker tailed distribution, right? And then suppose this part was 2.5 probability, and then this is a threshold value for the z. But in order to match the same probability value, or the area under the ROC curve, will the corresponding t value, t of alpha over 2, will it be to the right or left from this part? Left and right. Again, left. Okay. Yep. So the second case will be the true case, because we will have the same probability value. So it is a higher, right? Because it's a heavier tail or thicker tail. And so in order to have like the 2.5% of the probability, or the area under the curve, the threshold should be moved to the right. And that way, this amount, or the area, will be the same as this guy, right? And thus, given the same confidence interval, and also assuming that this guy was yeah, the true value was 5, but our estimate for the sample standard deviation was also shown to be 5. In that case, since that 5 is inaccurate, or that is an estimate value, we will generally have larger or the wider confidence interval, right? Which is a little bit bad thing, right? Because with in order to ensure the same confidence level, or 95% of the confidence level, and then this confidence width, or the length of the confidence interval, should get larger in general, just because we do not know exactly the true variance or the standard deviation, right? And that is mainly because, yeah, we have to apply the t distribution, which has a thicker tail than the standard normal distribution, right? Because of this figure. Okay, but the one caveat, or one kind of tricky thing is, this can be actually dependent on the your sample. What I mean is, it may not be always true that you will have a larger confidence interval, because S can change. So even though the true parameter for sigma was 5, your sample variance or sample standard deviation, even though their average will be 5, right? But that can be sometimes 4 or 3 or maybe 6 or 7 and so on, right? So if you happen to have a lower standard deviation estimate compared to the true standard deviation value, and then this will influence your the length of, or the width of the confidence interval, right? So if you get lucky and your sample has really small variance or standard deviation, and then accordingly you will have a quite narrow confidence interval in this case. So my point was, this part and also this part will be determined by your sample. So your confidence interval will be determined by these two factors, or two information. Yeah, we can do one-sided confidence intervals as well, right? So if it is an unbounded to the left, and then so our confidence interval is something like mu is some value less than some value. In this case, we have to put 5% of the probability on the right side, right? So in this case, we will just obtain, so we will put the alpha on the one particular side, instead of just distributing this 5% probability into both sides. Yep. Okay, then let's look at this example. It's just a simple application of what we learned just before. So our sample size is 16, and then their average value, or sample mean, is this value. And then their sample standard deviation is this value. So this squared value of this will be our sample variance, which was obtained by this n-1 sum of xi minus sample mean squared, and then we sum them up divided by n-1, which is in this case 15, right? Because our sample size is 16. Okay, and then we just apply this. So we require 90% of the confidence interval, so we put 5% on both sides, and thus, this is a 5% and the corresponding threshold value from the t distribution. and then we just multiply them with this sample standard deviation divided by the square root of the total number of samples. And then this t distribution, what is the degree of freedom of this guy? It should be n minus 1, right? So it should be 15. So you have to look at the table with this degree of freedom for the t distribution. So you just plug each values into these equation. In that way, you obtain this confidence interval. Any questions so far? Okay, then the next thing is a little bit of an interesting extension of what we learned, but it's more about kind of incremental or streaming kind of a scenario. So what I mean by this streaming scenario is as follows. Previously, we considered some sample that has a particular sample size, right? The particular number of observation. But in this scenario, we keep obtain, our sample gets added one by one. So suppose you obtained maybe 4 samples at this point, and then of course you can estimate some sample, the estimate or the interval estimate for the true mean value by using these 4 samples. But here the situation is a little bit different. What we want to estimate is the next sample that we will get based on these 4 known samples. Okay, so we want to have an interval estimate, not just for the true mean, but for the next sample. Okay, so this is a slightly different situation. So we consider this kind of statistic. So let's just ignore this part for now. So here the story is, what will in case you want to do you have to do a point estimate of the next sample. Okay, so here the scenario is all these x1 through xn, also xn plus 1 will follow the same distribution. Okay, IID situation is also true in this case. And then suppose you obtained this sample up to this point, and then what will be the best or the most reasonable point estimate for the next sample? So it is x1, x2, x3, x4. And then it will be, of course, the mean of the previous samples, right? That will be the reasonable choice of our point estimate. Okay, and then this guy is our such a point estimate, which is the sample mean of the previous sample. Okay, so it is the sample of these 4 data points, sample mean of the 4 data points. And then we are considering the difference between the actually observed value in the next time step, which is x5. Okay, and then we can consider what kind of distribution does this guy follow. Okay, and then let's think about this. And then this guy will follow the true parameter mu. So here the situation is each of your observation will follow some distribution, but their true parameter, true mean value is mu, and the true variance will be sigma squared. Okay, so the situation is still the same. And then this guy is just a sample mean, and thus it will follow the it's a Gaussian distribution with the true mean value as the true parameter mu and square root sigma over square root n, right? Then what about this guy? What about this guy? So each of your sample, I mean, we have to have one more assumption that each of your individual observation will follow the Gaussian distribution. So it is not just an IID, and each of them will follow the Gaussian distribution. And then in that case, yeah, the single one of an xn plus 1, which is this guy, x5, will also follow this Gaussian distribution of, yeah, this guy, right? So far so good, right? And then now this guy is just the difference between the two. So we just subtracted between the two. And then the what is the average? What is the average? Or the expectation of these the difference between them. So we apply this expectation operator to each one, and then yeah, it will be mu minus mu, which will be 0, right? So this guy will have a 0 mean, but what about the variance of them? What about the variance of them? So let me ask this question. Suppose x follows the Gaussian distribution of maybe 3 and 4 squared, and y will follow the Gaussian distribution with the same mean, but maybe different variance. And then what about the variance of these two? It's 4 squared and 5 squared. And at the same time, we need this term as well, right? But if x and y are independent, then this part will be gone. This part will be 0. And thus, yeah, the sum of these two variables will have this variance. The sum of the variance, the two variables variances. And what about this x minus y? It will be the same, but this part will have a negative sign, but they are 0. So yeah, it will have the same variance. Okay, and then in this case, okay, so up to this point, yeah, up to this point, yeah, we only need these. So we know these two, and also x, y are independent. Okay, so only these three facts will lead to these two. Okay, and now, yeah, so we can safely ignore this mean value. So even if they are different, these two will hold true. And then now we have an additional assumption that each of them are Gaussian random variable. In this case, this x plus y or x minus y will also follow the Gaussian distribution. Okay, so that was one property that you probably studied in the previous chapter. So Gaussian has a kind of a special property, so that the sum of the Gaussians will also be a Gaussian, and also this x minus y will also be a Gaussian, because if y is this, and then what about this minus y? What is this random variable's distribution? And then the mean value will be negated, but the same variance and the same normal distribution, of course, right? Okay, so x minus y can be trivially understood by using this from the perspective of this x plus y being still following the Gaussian distribution. Okay, so back to this scenario. Our conclusion, when xi's, each of xi's are following the Gaussian distribution, and their Gaussian distribution has the same mean and the variance, and then each of them will be this, and then x minus y will have also Gaussian distribution, and the mean value will be 0, because they are just same as the subtraction between these two mean. And then what about the standard the variance? Variance will be simply the summation of these two, right? So that is the point in this case. So x minus y, this guy, will have the variance of sigma squared plus sigma squared divided by n, which is 1 plus 1 over n times sigma squared. So this is our variance. Okay, and then yeah, this guy has a Gaussian distribution which has a zero mean, and then the variance is this value, and then the square root of them, and then we just divide this value by this, and then now this guy is finally a standard normal distribution. Okay. Okay. Yep. And then what do we have to obtain from here? So what are we doing here? We are obtaining the estimate, the interval estimate for xn plus 1, right? So this guy follows C, right? And then what we have to do is, like, this value should be z of alpha over 2, right? And then minus z of alpha over 2. And then we just clean them up or manipulate this inequality so that xn plus 1 has some range, right? And then this guy will be multiplied with this standard normal random variable, and then yeah, this guy will be added on both sides so that we obtain this. Okay, then let's think about this case. Suppose you have a so let's just compare this with the previous scenario where we obtained the interval estimate for sample mean. Okay, sample mean. So what was the difference? So in the case of sample mean, this part was mu, and then we will obtain yeah, this part was mu, and then this was in this place, right? But yeah, it was x bar minus mu, but it is the same thing essentially, even if we just put the negative sign, right? And then this part was just this, right? And then now this part will be this guy, right? And so it is multiplied with this z of alpha over 2. And so when n is the same, which one gives a larger interval estimate? So this or this? So does this have a larger interval estimate, or this guy has a larger one? The upper one. The lower one. Again, the upper one. Okay. Okay. If I saw correctly, only one student of just raised the hand. I mean, whether it's correct or not. So yeah, at some point we may have no students raising their hands at all in all cases. But anyways, in this situation, yeah, of course, this one will have a larger variance because, yeah, this guy and this guy. So this guy was sigma times 1 plus this, right? So, yeah, this value, yeah, will have a much larger value, right? and thus the larger value will be multiplied with this, and thus the interval width will be much larger, right? And then what is the reason for that? So how can we understand these differences? So the situation is that we still used the same sample, like x1 through x4, right? We still used the same sample, but in the previous situation, we wanted to have an interval estimate for the true mean value, okay, the mean value. But in this case, we wanted to obtain the interval estimate for the next sample, right? The next sample. Okay, so it can be understood in this manner. So yeah, so mean is still a kind of middle point of our distribution, right? Right? And then in the previous case, estimating the true parameter mean, true mean value is about where this mean value will be, right? And then in this situation, we are internally estimating this true parameter mean, and then we are actually estimating the possible sample, I mean one individual sample obtained from this distribution that has the mean value that we are estimating, right? So one individual sample, which is an x5, and this is what we are estimating in this case. So naturally, the middle value, which is our estimate of the sample, estimate of the true mean value, okay, compared to that, this individual sample will have a larger variance, right? And thus we have a larger confidence interval. And then what is the extreme case? What about the extreme case? So you obtained maybe 100,000 samples, okay? And then you are estimating just the next sample. And in this case, which one goes to 0? This guy will go to 0, right? This guy will go to 0. And then what about the corresponding variance or standard deviation? It will be converging to the true standard deviation value, right? And so compared to this situation, you can understand this situation as follows. So if you perfectly knew the true mean value of mu, and then you can probably estimate your next sample or x5 or 100,000 plus 1. I mean, the confidence interval will be exactly the same as this true standard deviation, right? But in this situation, we do not know the mean value, right? So we don't know where the exact mean will be, right? So it can also shift around, it can move around, and thus that kind of uncertainty factor will add the variance to your individual sample, and how much variance will be added, that will be this amount, right? Because in this situation, it will be just a sum of sigma, which is an original standard deviation of the individual sample, and then you will have an additional standard deviation by this amount. Okay. And then now we are still doing this prediction interval, or predicting the interval, obtaining the interval estimate for the next sample. But the situation here is we do not know the true variance. In that case, we just use a sample variance, and then instead of using the true standard deviation sigma, we are using the sample standard deviation, okay? And then magically, this one will follow the t distribution, but the degree of freedom will be n minus 1, right? So yeah, we are using this t random variable, and then yep, we obtain almost the same interval estimate, but we are using t, but also we are replacing the true standard deviation by this sample standard deviation. Okay, let's look at this example briefly. So it's still a prediction interval kind of context, and then these are the 7 samples that we obtained so far, and then we consider the interval estimate for the next sample, and then by using that we can obtain sample mean and the sample variance, and then given this confidence interval, we obtain this t of alpha over 2, and the degree of freedom will be 6 because we have 7 samples, so n is 7. And then now our sample variance will be plugged in the place of this true standard deviation position, and then by using that we can obtain this interval estimate for the next sample. Okay, and then let's look at this this situation. So you understand what this is, right? And then let's consider that you keep estimating the next sample one by one. Okay, so up to this point you have 4 sample, and then you are estimating your 5th sample. Okay, and then now you have your estimate, interval estimate, but in the next day you will obtain your actual sample x5, which is just a particular value, right? So it can be within our interval estimate or not, right? But anyways, suppose you obtained another sample in the next day, and then now you have 5 samples, and then now you are estimating the 6th sample in the next day. Okay, and then in that case the mean value will also be shift, right? Because this sample mean, or this guy, will be updated as you get more and more samples. But what about this one? This value? This value will keep decreasing. So the interval width will keep decreasing, right? But what about this case? What about this case? So of course, your sample mean will change, and thus the middle point as your estimate for the next sample will also change. So that is the same as the previous situation. But in the previous case, as you get more and more sample, you get a more and more confidence in the next sample in terms of the interval width, because interval width will be smaller and smaller as you get more and more sample. But what about this? What about this? This guy changes, but also this sample variance will change as you get more and more sample, right? So in this situation, suppose you obtained like 3, 6, 5, 4, and then up to this point you will have some value of standard deviation or sample variance, right? And then in the next, you will have some interval estimate for the 5th sample. But in the next day, your sample was really surprisingly a little bit far from those values. For example, like 10. Okay, and then you have to modify your estimate for your sample variance or sample standard deviation, right? So in the previous case, you are given the true variance value or true standard deviation value. So that was our assumption. But in this case, we have to estimate that standard deviation or the variance, right? So those estimation or sample variance will be determined or computed by our sample. So if we saw really large largely deviated value, and then we have to kind of modify our estimate or our guess about what the sample variance, what the true variance or what the true standard deviation will be, right? So in this case, the next sample's confidence interval width will be larger, right? So that is another hopefully interesting kind of aspect, right? So in the previous case, again, the interval estimate will get smaller and smaller. And in this case, it can be smaller. In general, it will be decreasing, but it can be sometimes kind of larger than the previous one. Yeah, so this kind of scenario is quite widely used in practice. So yeah, it is basically a prediction based on your previous data, right? So yeah, it has really having a machine learning kind of flavor. So you have a bunch of training data where you can obtain some useful information from, and then also you want to predict what will happen in the future. Okay, and then in this case, as this time index or sequence index n will increase, right? So we are considering where these n have some kind of ordering kind of notion. So it can be viewed as a time. So one day, yesterday, today, and then tomorrow, the day after tomorrow, and so on, right? So it can be considered as a kind of sequential or temporal kind of data situation. And then, there are many interesting kind of techniques based on this kind of ideas. And then one interesting application will be some kind of a missile tracking a particular object. Okay, so you launch the missile, and then your goal is to hit some moving object, which can be like a hostile airplane or something like that, and that will keep moving around, right? And then your missile will keep obtaining some information based on some vision or this camera kind of this visionary information based on some camera or based on some kind of radar. So yeah, you emit some kind of radio kind of signal and then get some responses to identify or to understand where the target object, the exact position of the target object. Okay, and then okay, so you understood this guy was placed, or the position of the target object was around here. Okay, and then you are kind of modeling this guy's behavior, and that guy's behavior is corresponding to some Gaussian distribution in this particular example, and then you want to estimate some kind of underlying parameter that will determine this Gaussian distribution. Okay, so if you correctly estimated the underlying but unknown parameter that will determine the moving behavior of this target object. So based on this, we estimated the sample variance to be a little bit small value, and then based on that, we obtained this interval estimate, which is a kind of a really narrow or very good kind of interval estimate. But suddenly, our prediction was quite wrong, right? In that case, we have to adjust our estimate of the model parameter, and that model parameter in this case corresponds to this larger sample variance. Okay, and then this kind of adjustment can be applied to the parameter of the variance itself, but also it can affect your estimation of the other parameters, such as a mu value, and also if your distribution or the distribution that you are assuming on this target object's movement can be a different distribution. It can be maybe exponential distribution or Poisson distribution, or maybe some even more complex distribution. And in that case, it may have a little bit more parameters, not just these two, like a mean and the variance, but also you may have a little bit more number of parameters. And then this kind of behavior will affect your estimation of all these parameters. And then so when it comes to this problem, still, yeah, it is often the case that you apply the Gaussian distribution, because Gaussian distribution can reflect a lot of natural kind of physical kind of objects behaviors. So Gaussian distribution is a kind of a good thing that you can apply in many different, yeah, many different kind of behaviors or something like that. But even if you, yeah, so let's consider kind of Gaussian distribution in order to predict the next movement. But in this case, yeah, it is already kind of two-dimensional random variable because we have an x-axis, y-axis, and also this guy, yeah, we are living in the three-dimensional space, right? So what we have to predict in terms of is this variance of an x can be viewed as cov of x comma x, right? So you can have like three different choices in the place of these two input argument for covariance. So if you have a three-dimensional Gaussian distribution, and then it can be viewed as, yeah, the variance will have the number of parameters as like 9. Okay, but here, yeah, what is this cov of x comma y and cov of y comma x? They will be the same thing. So the order doesn't matter when computing the covariance, right? And so yeah, essentially, yeah, we have a 3, and then yeah, x and y and z, their variance, and then the 3 to c. So altogether, you will need these number of unknown parameter that you have to estimate. Okay. So even when you just apply simple Gaussian distribution when modeling the target object's movements, then you will need that much of numbers to estimate. Yeah, since it is a really important concept, but may not be that much intuitive or may not be easy to understand, but it is really widely used, this multivariate Gaussian distribution. So let me just do I not have a Wi-Fi? Uh-oh. Yeah, this doesn't have it either. Okay, I think I got connection. Okay, so this is the formula for multivariate Gaussian distribution. Yeah, so it's a little bit scary, but yeah, I don't think I can explain it in detail, but yeah, in the later time, you may have some chance to study this in more detail. Okay, but yeah, it can be viewed as this. So we have this part. So it can be viewed as like a x minus mu squared, right? X minus mu squared divided by 2 times sigma squared, right? So that was the inside of this exponential part, right? So this part and this part is like a squared of x minus mu. And then what about this sigma inverse? Sigma is the matrix which contains all the variance or covariance numbers. So as I mentioned, when having 3 variables, we have to consider the covariances between all the pairs, including the same one, right? So that kind of information can be modeled as, like how? Okay, so we prepare for these 3 by 3 matrices, and this guy is just a variance of x, or covariance of an x comma x, and this guy is covariance of x comma y, because this x and corresponding to y, and this guy is covariance of x comma z, right? So that way you can put all these all the possible covariance values into this single matrix, and then so we had this, right? And then now you can think of like this, multiplied by sigma squared, but this sigma squared will be just a scalar variance, but now your variance is just a matrix, so dividing something by scalar number is corresponding to like sigma inverse. So sigma inverse is placed here, sigma inverse, which is corresponding to like the thing that divides something by this is scalar sigma squared, and thus you have to obtain this inverse matrix, and then we have a 3 by 3 matrix, right? And then we have these 2 vectors, but now we have a vector, right? 3-dimensional vector, current x comma y comma z, and the mean vector of an x comma y comma z, right? Then we can transpose it of this vector into this row vector, which is like a transpose, and also this vector as a just original column vector as this. So it is like x minus mu transpose, and this guy is sigma inverse, and this guy is x minus mu. And then after doing this computation, what is the size of the resulting value? Will it be a vector or a matrix or a scalar? So you just imagine this vector matrix vector multiplication. What would that value be? What would be the size of it? What would be the size? Yeah, it's a scalar, 1 by 1 value, right? So that 1 by 1 value will be, placed here in the exponent part. Okay, so altogether, so even though you have a 3-dimensional vector, your probability density function should give a scalar probability density value, which is a scalar value, right? So this guy is computing that scalar value, right? So still, in this case, it is even though it is really a complicated operation, but at the end we will obtain the scalar, and then that will work as this exponent of this expression. Yeah. So it is quite an interesting extension, and if you can properly understand it, and then I think you can do a lot more interesting stuffs and understand interesting stuffs in machine learning and statistics and so on. Okay. Any questions so far? Then the next topic is about this estimation of the variance. Okay, the variance itself. So of course the variance is assumed to be unknown, right? Okay, and then you consider the sample variance, which is the unbiased estimator, right? And then n minus 1 sigma and xi minus x bar squared. So this is the representation or expression of our s squared, right? And in this case, like, yeah, so again, if we replace this guy as mu, and yeah, let's just divide it, remove it, and then we replace it, replace it by this sigma squared, and then that will follow the chi-square distribution with the degree of n. Is it right? It is summing over I from 1 to n, right? And then now the story was, instead of using the true mean, which we do not know, right, we replace it by our sample mean, right? And then this same representation will follow the chi-square distribution, but with one less degree of freedom, right? Yep. So far so good, right? Okay, and thus we have this, and then we put here, and then we just cancel this out by multiplying that, and that will follow this chi-square distribution, right? Yep. Okay, then we can obtain this interval estimate. Okay, what is the general kind of shape of the chi-square distribution? It was something like kind of this, right? Okay, then let's remember. Yeah, in the case of chi-square distribution with the degree of freedom of an n, what was the mean value? What was the mean value? Oh, yeah. Mean value was n, right? And then what about the variance? It was 2n. You should have you must have memorized it when preparing for your exam, right? Okay, so it gets wider and wider, and then the mean will be shifted, right, to the right. Okay, and then yeah. Okay, and then this value will have the mean value of n minus 1, and then the variance as 2 times n minus 1, right? And then suppose we require 95% of confidence interval, and then we just distribute this probability half and half, right? And this value is, yeah, this value is represented by this chi-squared and this guy and this, right? And then what about this value? What about this value? This value. Okay, then it will be like this value can be represented as, so this part will have 2.5 probability, 2.5% of the probability, and thus this part will be, yeah, 1 minus alpha over 2, which is a 97.5% probability, right? And that will be our threshold value on the left, right? You can easily understand that, right? Okay, so that's why we obtain this. Okay, and then we have to manipulate this expression in terms of this sigma squared, because that is our parameter to estimate. And then this guy and this guy will be our boundaries, or the threshold on the left and right for our interval estimate for the true variance. Any questions? So here, the table that you have to look at is just the chi-square distribution, right? Okay, so here you need it. Yeah, you are required to have a 90% of the confidence level, and then you have to put 5% on each side, and thus we have to obtain this value and also this value. And 9 comes from the fact that we have a 10 sample. Okay. Okay, it's the same thing. Yep. Any questions so far before moving on to the next part? Okay, then the next part, which is still the part of chapter 7 is about this estimating the difference between the two distributions. Okay, so now we consider the two distribution. So for example, like so we have some products like an iPhone, for example, manufactured by like factory 1 and from another factory, and then our primary interest is whether they have actually the same defect ratio. So for example, this factory is much kind of a lower quality, and then they may produce a lot more defective items, right? Or vice versa. Or or these two factory may have exactly equal kind of quality of this manufacturing kind of level. So in that case, those two will have the same kind of defective ratio, right? So we are kind of interested in this kind of problem or answering this kind of question. Okay, so we consider these are two different normal distribution and obtain like two sets of samples. So one sample obtained from one population or one distribution, and then the other sample from another population or another distribution. Okay, and then suppose they have their own mean and the variance, and the sample size in the case of first factory was n. So you obtained maybe 10 iPhones from one factory, and then you obtained maybe 30 iPhones from the second factory, and the second factory has its own mean and the variance value. And now you are interested in the interval estimate of this guy, v1 minus v2, which is a kind of difference, average difference in terms of this defective ratio, or the number of like a defective iPhone cases. Okay, then if we were to use a point estimate, the reasonable estimate of these two will be like x1, x bar minus y bar, right? So that is the reasonable point estimate, but we are considering interval estimate, right? So if we are considering this defect ratio, and then it is corresponding to like a probability. So we want to estimate the probability. But now let's think of this example as like so what is the mean the true mean difference between the men's and the women's height? Okay, so men will have their own distribution in terms of height, and women's height will also have its own distribution, right? So we have two Gaussian distribution, and what will be the difference between the true means from these two distributions? So that is corresponding to, where is it? This guy. We want to estimate that guy, okay? And then this is our reasonable estimate, point estimate, but we are considering its distribution, and that way we want to obtain the interval estimate, right? And so this guy will follow this Gaussian distribution and this, right? And then this guy, which is kind of similar to like a prediction, interval prediction, or prediction interval. So these two are of course independent, right? And then they are Gaussian distribution, because individual xi's and individual yi's are Gaussian, and thus their mean will also be Gaussian. And then this statistic will have also a Gaussian distribution, because the subtraction or the summation between the Gaussian distribution will also be Gaussian. and thus the mean and its mean value will be mu1 minus mu2, which is a true parameter based on the true parameter value. And what about the variance? It will be just simply the sum of these two random variables variance. So we are adding these two, right? Yep. Okay, and then you can obtain the interval estimate of these two, right? Or in this case, yeah, what you are obtaining is x bar minus y bar will follow the Gaussian, minus mu1 minus mu2 as a mean, and then this guy and square root of this guy, right? That will follow the standard Gaussian distribution, and then we are like forming this inequality and then manipulate it so that your inequality will be represented in terms of mu1 minus mu2 that has a lower and upper bound, or this interval estimate, right? Yeah, I'm not sure what is this? So this is not about the two different samples. It's about just a single sample that we discussed in the previous part, right? But anyways, it's just a summary kind of table. Okay, now, yeah, this is on track. Okay, so this is a variance, and then we can manipulate it in a way that we have this form. Yeah, the remaining story or scenario will be the same, and then we can also apply the one-sided interval. And then now let's extend this case when we do not know the variances of each of these two Gaussian distribution. Okay, so in that case we have to use this sample variance from each population or each sample, like sample variance from the men's height and the women's height, and then just we simply replace these two values as our estimate value. Okay, and then as we will kind of study the derivation of it, but what kind of distribution can you expect it follows? What kind of distribution will it be? It will be like T distribution, and then the question is, what will be the degree of freedom? What will be the degree of freedom? It's just a guessing game. Let's make a guess. So each one had, if we were considering each sample, and then x size will follow, so this guy will have the degree of freedom of n minus 1, and the y will have the degree of freedom as m minus 1. And then we somehow subtract it together, right? So in that case, what will be the degree of freedom? So you involve, it can be viewed as something like this. I mean, it will be more kind of intuitive. So in that case, you are adding the two uncertain kind of measurement into one, and then such kind of uncertainty will get bigger. Right? And then, so basically more number of random variables or random entities are involved in this. So you can think of it as having this guy has a kind of random n-1 random variables involved in it, and this guy has m-1 random variables involved in it. And then, altogether, it will have this number of random variables involved in it when forming the t-distribution corresponding to this statistic. Okay? So this is just an kind of intuitive guess or kind of a reasonable guess that we are trying to do. Okay? So this is our conclusion, but we have a really nice and clean kind of proof to lead us to this conclusion. That will be these. And yeah, we will discuss it next time. Okay, thank you very much.
It's not related to class, but when is the last day of class? Last day.
Yeah, it's the last day will be 15th of December, I think.
시험은 그 21일이요.
아마 화요일에 보려고 하고 있어요. 이게 21일인가요, 그게? 네.
근데 21일은
네.
are there going to be more exams after the 21st or not?
Was that after 21st, you said?
Is there more exams or is it the first and last day?
Yeah. I mean, at least for our class, we will have just one day of an exam, right?
학점이요. 절대 평가인가요?
네?
상대 평가요.
절대 평가이긴 한데요. 거의 좀 상대 평가처럼 이제 좀 줬었.